Welcome to some more remote learning. Today we're going to be going over the comparison tests for Calc 2. And for those of you that don't know me, I'm the tutor in the math help room at the Academy. What we're going to be doing today is covering not just the comparison test, but also the limit comparison test, and I'm going to be providing you examples and practice problems to help with your online education. So let's go ahead and jump into this. Now, this should be a review, but let's go over it real quick. The comparison test says let some summation of a sub k and some summation of b sub k. So let those be series with positive terms. So if your a sub k series and your b sub k series is what you're comparing it to, looking at this first part, if a sub k is indeed less than or equal to b sub k, and we know that the series of b sub k converges, then a sub k also has to converge. For the second chunk, it says that if b sub k is now less than or equal to a sub k and b sub k diverges, so now we're saying that a sub k is actually greater than this b sub k, then we know that a sub k diverges. So two different potential options for this comparison test. So let's go ahead and look at example 1 to help us figure out how this works. So we're going to consider the series 1 over k squared plus 10. And that's the summation from k equals 1 to infinity. I labeled this here for us saying that that's our a sub k series. So we need to figure out some b sub k to compare it to. And the way you choose what to compare it to is, what I like to do, is take the highest powers from the numerator and the denominator. So in our numerator, we just have a constant of 1, so I'll leave that. And then in our denominator, what's dictating the growth of that, what's really influencing that growth, is not this 10. It's going to be this k squared. So the series that I will compare it with, my b sub k, is going to be the summation of k equals 1 to infinity of 1 over k squared. And the next step is to figure out what b sub k is doing. We created this comparison series so that it's something we'll easily be able to tell what happens with it. And it's either going to converge or diverge. But if you notice, the b sub k that I created is a p series, and this is a p series with a p-value of 2. And because 2 is greater than 1, we know that this p series converges. So I'm going to say, therefore, our b sub k series converges. So looking at the fact that b sub k converges, we're looking at number 1. So what do we want to show? Because b sub k converges, we want to show that a sub k is less than or equal to b sub k. So my a sub k is 1 over k squared plus 10. And I'm going to be comparing that with 1 over k squared. Now, our numerators are the same, but our denominators, if you look at the denominator, our a sub k denominator is going to be bigger, because we're adding 10, than our b sub k denominator. So because the denominator is bigger, that makes the overall fraction smaller. So this is going to be less than 1 over k squared. So, because, and I'll go ahead and write this out real quick. So, because a sub k is less than or equal to b sub k, and we knew that b sub k, that series converges, then we can say that a sub k, our series 1 over k squared plus 10, also converges. So we know that our series converges. Let's go ahead and jump into example 2. Now example 2, we're considering the series a sub k, let me go ahead and zoom in a little bit for you guys, where we have 1 over the square root of k minus 3. What we're going to look at is, well, we have to find a comparison, and a comparison that we know what's happening with it. So in our numerator, what's not changing is 1. So I'm just going to rewrite 1. But in our denominator, what's really dictating the growth of our function is this square root of k, not this minus 3. So in my denominator, I'm going to write the square root of k. So this is the series we're going to compare it with. And the nice thing about this is that that's a p series where the value of p is equal to 1/2, because the square root of k is the same as k to the 1/2. Therefore, since it's a p series with a value of p is 1/2, and that's less than or equal to 1, we know that b sub k diverges. So because we know that it diverges, let's scroll back up real quick in our examples. Because it diverges, now we're looking at not number 1, so let me go ahead and erase this. We're looking at number 2. Alright, so now looking at the second part of the comparison test, we just discovered that our series b sub k diverges. So because b sub k diverges, what we want to show is that b sub k is less than or equal to a sub k. If we can show that, then we can conclude that a sub k also diverges. So, scrolling back down to our example, we got that b sub k diverges, so now we're going to compare a sub k with b sub k. So now a sub k, which is 1 over the square root of k minus 3, we're going to compare that with 1 over the square root of k. If we look at our numerators, the numerators are the same. We have 1 and 1, so because they're equivalent, all we need to do is look at our denominator now. So the denominator for a sub k, we're subtracting 3 from k and then taking the square root of it. Whereas in b sub k, we're just taking the square root of k. So that makes the denominator over here smaller than the denominator for our b sub k. So because the denominator is smaller, the overall fraction is larger. So because, and I'll go ahead and write this out, so because a sub k is greater than b sub k and b sub k, that series diverges, then our series of a sub k, which is 1 over the square root of k minus 3 from 4 to infinity, also diverges. And that's how the comparison test works. If we show that our b sub k, our comparison series, diverges, we need to show that a sub k is bigger than that thing diverging. And if b sub k, that series that we're comparing it with, converges, then we want to show that our series, our original a sub k series, is smaller than that thing that's converging. So let's jump into more practice problems going through the comparison tests. So, for practice 1, it says use a known test to determine whether the following series converge. Now, I'm going to write out my a sub k. That's going to be 3 over 2 plus e to the k. Now my b sub k, what I want to compare it with, well, my numerator is just a constant of 3, so I'll leave that as is. In my denominator though, what's really dictating the growth of my function is this e to the k. So for my b sub k, I'm going to have 3 over e to the k. Now if you see b sub k as a series, which I'll go ahead and write over here, the summation of b sub k is going to be the summation from k equals 1 to infinity of 3 over e to the k. So I'm going to rewrite the summation to make it a little more clear what we have. I'm going to pull this 3 down in front of my 1 over e to the k. But as opposed to writing this as 1 over e to the k, I know that 1 to the k is still 1. So I'm going to write this as 1 over e all raised to the k. And from here, you should recognize what kind of series is this. If not, we should go back and review some of our geometric series, because this is a geometric series, and geometric series are in the form of a r to the k. So our r value for this geometric series is 1 over e. And I know for geometric series, if my r value is between -1 and 1, I'm going to converge. So, because 1 over e, which is 1 over 2 point something, that's a fraction that falls between -1 and 1. Therefore, because -1 is less than 1 over e, which is less than 1, I know that my b sub k is going to converge. So if I know that b sub k converges, I need to show what? Well, if b sub k converges, I want to show that a sub k is smaller than b sub k. So if I look back up at my a sub k, 3 over 2 plus e to the k, and I compare that with 3 over e to the k, you can see my numerators are the same, but my denominator for a sub k is bigger than b sub k, which makes my overall fraction smaller. So, because a sub k is indeed less than or equal to b sub k, and I showed that my series of b sub k converges, then I can say that a sub k, which is, I'll go ahead and rewrite it, from k equals 1 to infinity of 3 over 2 plus e to the k, I know that that converges as well. Let's move on to b. So b is a little different because now we're throwing in a log. We have 1 over k squared times the ln of k. So choosing the comparison series is going to be a little bit trickier, but we know that the ln of k, if we're just looking at that, because we're starting at a k value of 3, the ln of 3 is greater than 1. So we know that the ln of k is always going to be greater than 1. And we also know that the ln of k, by growth rates, is always going to be less than k. So a good comparison for this, if a sub k is 1 over k squared times ln of k, a good comparison for this would be b sub k as 1 over k squared. So the summation from k equals 3 to infinity of b sub k, which is 1 over k squared, I know that that's a p-series where p is equal to 2, which is greater than 1. Therefore, the summation of b sub k, our b sub k series, converges. So because b sub k converges, for the comparison test, all I have to do is show that a sub k is smaller than b sub k. And that's where this helpful inequality that I wrote comes into play. Because if 1 is less than the ln of k, which is always less than k, the ln of k is going to be some positive number greater than 1. So when we're looking at 1 over k squared times the ln of k, because we're multiplying k squared by a number bigger than 1, that denominator is going to be greater than just k squared, which makes this overall fraction smaller. So because a sub k is less than or equal to b sub k, and we showed that our series of b sub k converges, then our series for a sub k also converges. And again, quickly, how I chose to compare it with 1 over k squared, because if I wrote the ln of k as 1, this would be 1 over k squared. And if I wrote it as k, then that'd be 1 over k cubed. And I know I'm falling somewhere in between those, so it's going to be easiest to compare it with 1 over k squared. And if you're confused on how I chose that comparison, double check with your textbook because there's other examples using logs within that. But for now, let's continue on to c. So looking at c, we have k cubed plus 4k over 2k squared from k equals 1 to infinity. So if you were to jump into this, starting with the comparison test, you're going to do so much work to get the right answer. This is not comparison test at all. That's why when I listed this practice, I said use a known test. So a little bit of a trick here. What we can do for this to figure out whether it converges or diverges is simply the divergence test. So don't do more work than you have to. Lots of times I'll just do the divergence test in my head before I jump into any other test because the divergence test should be something that's easy just to think about without writing it out. But writing it out so that you can see the limit as k approaches infinity of k cubed plus 4k all over 2k squared. Looking at our highest power rule, we have k cubed over a k squared. That's going to go towards infinity, which doesn't equal 0. Therefore, by the divergence test, this series diverges. And this is a good problem because if you're given a test or a quiz and you have a bunch of series and they say, hey, figure out whether this converges or diverges, even though this looks like a very, very good case for a comparison test or a limit comparison test, which we're going to jump to in a second, do the divergence test first, because if you can figure it out in 2 seconds versus figuring it out in 10 minutes, one of those is going to be more advantageous for your time on a test. So always do the divergence test first in your head. Now let's go ahead and move on to the limit comparison test. And the limit comparison test I consider almost a little bit of an extension of the comparison test. I think it's actually a stronger case. So unless I know for a fact that I'm smaller than something that's converging, or my original series is bigger than something that's diverging, the limit comparison test is a good test to choose. What the limit comparison test does is it allows us to take our series of a sub k and our comparison series of b sub k and set up a ratio between the two. And the limit of that ratio is going to equal some value L. So if L is a finite number between 0 and infinity, whatever b sub k did, then a sub k does the same exact thing. But if we get L equals 0 and b sub k converges, then a sub k converges. Or if we get that L equals infinity and b sub k diverged, then a sub k diverged. So let's go ahead and jump into number 3. In number 3, it says use the limit comparison test to determine whether the following series converge. So just like choosing the comparison when we did the comparison test, we're going to look at those higher powers. So I'm going to say that my a sub k is going to be equal to k cubed over 2k to the 4th plus 2. So my b sub k is going to be, in my numerator I have k cubed, and in my denominator my highest power is that k to the 4th. So I'm going to leave this as 2k to the 4th. So if we were to do the comparison test first, notice that it's going to fail us. Because if I tried to compare a sub k, which is 2 cubed over 2k to the 4th plus 2, with k cubed over 2k to the 4th, do I want this to be bigger? Do I want my a sub k to be bigger or smaller? Well, let's decide what b sub k actually does. The summation of b sub k, which is k cubed over 2k to the 4th, from k equals 1 to infinity, I'm going to rewrite that as opposed to k cubed over 2k to the 4th, I'm going to pull my 1/2 out in front, and k cubed over k to the 4th is going to be 1 over k. And that's going to go from k equals 1 to infinity, which this is a p-series, or our harmonic series, because it has a p-value of 1, which is less than or equal to 1. Therefore, our b sub k diverges. So because we know b sub k diverges, for the comparison test, it would be really advantageous for us to show that a sub k is greater than b sub k. Unfortunately, because our denominator is greater, that makes our overall fraction smaller. So now we're smaller than something that's diverging, which, based on the comparison test, we don't know what to do with it. That's when we jump into the limit comparison test. So, without even needing to show whether one series is bigger or smaller than the other, we'll just take the limit of a sub k over b sub k, which is k cubed over 2k to the 4th plus 2, all over k cubed over 2k to the 4th as k approaches infinity. Rewriting this, some of you like to say keep, change, flip. I like to say when dividing by a fraction, we're just simply going to multiply by the reciprocal. So the limit as k goes to infinity of k cubed over 2k to the 4th plus 2 times, flipping that fraction, 2k to the 4th over k cubed. Notice now that my k cubes cancel out, and I have 2k to the fourth over 2k to the fourth plus 2. The limit of that is going to be highest power rule, take those coefficients, 2 over 2, which equals 1. So because 0 is less than 1, which is less than infinity, scrolling back up so we can see, we're at the case of number 1, where we got L for our limit, because L is 1, which is a number between 0 and infinity, which means that they both do the same thing. So they both behave in the same manner. So they're both going to either converge or diverge. And because we already showed that b sub k diverges, then a sub k is also going to diverge. So by the limit comparison test, because the limit as k approaches infinity of a sub k over b sub k equals 1, and 1 is a number that falls between 0 and infinity, we know that our series are going to do the same thing. And because b sub k, that series diverged, then the summation of a sub k, our original series in part A, also diverges. So let's go ahead and jump into B. Now if this is my a sub k, then my b sub k, I'm going to compare that with, well, my highest power here is k to the fourth, so I'm going to have 5k to the fourth over, here is 2k to the sixth. And this is a perfect example of if I was trying just to do the comparison test, and I have 5k to the fourth minus 2k squared plus 3 all over 2k to the sixth minus k plus 5, and I'm comparing that with 5k to the fourth over 2k to the sixth. Well, first of all, my numerators aren't the same, so this numerator is actually going to be smaller than this numerator, and my denominator is also going to be smaller, which makes it seem like the overall fraction is going to be bigger, but then there's this issue with the numerator being smaller. It just gets really messy. So this is a good case of just to jump straight into the limit comparison test and not even think about the comparison test, because there's not an easy way to compare it. So let's first figure out what b sub k does. So if I have the summation from k equals 1 to infinity of my b sub k, I'm going to rewrite this to make it easier though. So I'm going to bring that 5 halves out in front, so all I have left is k to the fourth over k to the sixth, which simplifies down to 1 over k squared. I know that this is a p-series, and my p-value is equal to 2, so because that p-value is greater than 1, we know that the summation of b sub k converges. So again, since I showed that it's kind of hard to actually compare those two, let's jump into that limit comparison test. So I'm going to take the limit as k approaches infinity of a sub k over b sub k. Now in this case, writing this all out as a fraction is going to be rather messy, so I'm going to write my a sub k over my b sub k as my a sub k, 5k to the fourth minus 2k squared plus 3 all over 2k to the sixth minus k plus 5. I'm going to, as opposed to dividing by my fraction b, I'm going to multiply by its reciprocal, keep, change, flip. That's going to be 2k to the sixth over 5k to the fourth. So now when I write this limit out, the limit as k approaches infinity of my two fractions multiplied together, I'll need to distribute this 2k to the sixth to all of my terms in the numerator. So 5k to the fourth times 2k to the sixth is going to be 10k to the 10th, because I add those exponents. And then 2k squared times 2k to the sixth is going to be 4k to the 8th, and then I'll add that to 6k to the sixth. 3 times 2 is 6, and then I'm multiplying that by k to the sixth. Now, next, I'll go ahead and distribute that denominator through. So 5k to the fourth times 2k to the sixth, let me make this fraction bar a little bit neater, is going to be 10k to the 10th, and then 5k times 5k to the fourth is going to be 5k to the fifth, and 5 times 5k to the fourth is going to be 25k to the fourth. Now, if I'm taking the limit of this, I really only care about those highest powers. 10k to the 10th over 10k to the 10th, that's 10 over 10, which equals 1. So because I got a finite value between 0 and infinity, that means that a sub k and b sub k, those series behave the same way. So because we already showed that b sub k converged, and for my limit comparison test I got a value of 1, I know that a sub k, that series, is also going to converge. So, writing this out for you, so we got converges in part B. So in part A, we did the limit comparison test and got that we diverged. In part B, we did the limit comparison test and got that we converged. Now for both A and B, when we took the limit of a sub k over b sub k, we got some finite value L between 0 and infinity, which means that those series behave the same way. But there's two cases we didn't even really touch on, and that's 2 and 3. If we get that L equals 0, or if we get that L equals infinity. And these two cases occur when we do the limit comparison test where b sub k converges and a sub k was a series that was smaller than that b sub k. Or if b sub k diverged and a sub k was a series that was bigger than that series that diverged. Because think about setting up those ratios, when we do the limit of a sub k over b sub k, if b sub k is something that converges and a sub k is smaller than that, taking the limit as k approaches infinity, we're going to go towards 0. Where with 3, if b sub k was something that diverged and a sub k was bigger than that b sub k, then our limit would go towards infinity. So let's try doing the limit comparison test with something that we know according to our comparison test. So let's just go ahead and do this with part B. So in part B, by the comparison test, we knew that a sub k was indeed less than b sub k, and we showed that b sub k converged. Therefore, a sub k also converges. But let's assume that you didn't know that 1 over k squared ln of k was less than 1 over k squared, because that could be a tricky thing to figure out. So let's go ahead and erase this and say, okay, so we don't know exactly how a sub k compares to b sub k. We can always jump right into that limit comparison test. So instead of performing the comparison test, let's do the limit of a sub k over b sub k as k approaches infinity. Then that's going to be the limit of 1 over k squared ln of k all over 1 over k squared as k goes to infinity, which I'm going to write as the limit as k approaches infinity of, for our fraction, we're going to keep, change, flip, or what I like to say, we're going to, as opposed to dividing by the fraction, we're going to multiply by its reciprocal. So we'll have 1 over k squared ln of k times k squared over 1. Note that k squared cancels out with k squared, so I'm left with, I'll write this out, the limit as k approaches infinity of 1 over the ln of k, which the ln of k is a function that continues to grow as k approaches infinity. So this is going to be 1, some constant, over a number that's blowing up, getting larger and larger and larger, meaning that our overall fraction is getting smaller and smaller and smaller, going towards 0. So we did the limit comparison test. We got that the limit was 0, and scrolling back down to that limit comparison test box, we got that the limit's 0, and we know for a fact that b sub k converges. We know that series converges because it was a p series with a value of 2, which converged. Then a sub k converges, which was confirmed when we originally had just done the comparison test. So for 2 and 3, you would get those outcomes if it was something that you could have shown with just the comparison test. But again, sometimes the comparison test is a little hard to exactly see what's happening, so the limit comparison test, you can always just jump into that, even if you're not sure of how those series compare, or even if you know exactly how those series compare. It's just a little extra work, but as long as you're choosing the correct comparison, the limit comparison test will show you whether your series converges or diverges. As far as personally how I like to do it, I like to always try the comparison test first because it's less work than the limit comparison test, but if I'm not sure how those series then compare, I'll go into that limit comparison test. But feel free to just go ahead and start with the limit comparison test. But for now, hopefully this video helped clear up any questions. If you're still confused on any of my work, go ahead and leave a comment for me, and I or one of your peers will respond. So until the next video, good luck.